Hi, I'm Norman Wildberger. In today's video, we're going to look at the classification of the Platonic solids, which goes back, of course, to Euclid's Elements, where he showed that there are exactly 5 regular solids: the tetrahedron, cube, octahedron, icosahedron, and dodecahedron. Unfortunately, Euclid's argument is not really complete. There are logical difficulties with Euclid's setup of spatial geometry, and there's several aspects of the classification which really are somewhat logically problematic. The task was taken up much later by Cauchy in the 19th century and others, including then in the 20th century, Coxeter, who wrote a very famous book on the regular solids going beyond the Platonic ones. But I think it's probably fair to say that currently all geometric arguments towards this classification are in one way or another incomplete. They run up against difficulties having to do with the continuum and the actual underlying framework of space that we need in order to create such a theory. So that's really more a topic that I should be talking about in the Math Foundation series. So I'm not going to go too far in this direction, but today I want to at least show you what the historical sort of argument is, but I don't want you to get the impression that the argument that I'm showing you today is actually logically completely correct. It's not. Okay, there's, however, these days also a combinatorial approach, which is very different to the geometrical one, where we think about what something like a cube or a icosahedron is in a very sort of graph theoretical sort of combinatorial approach. And there's a more discrete possibility of being more precise. Okay, so let's have a look at the basic idea of Euclid, which involves angles. And we're going to sort of rephrase this argument in a sort of a modern, more efficient setting, but this is the essential idea. So when we're talking about angles, we've talked before that it's more convenient to normalize our notion of angle so that going around once counts for 1 rather than some other rather arbitrary unit. And when we measure angles that way, we'll refer to this as being a turn angle, or maybe even a tangle if we want to shorten things more. So for an equilateral triangle, there are these 3 turn angles, and we'll have them sort of going in the positive direction. The basic orientation is that this is the positive direction and this is the negative one. So here there are these 3 equal turn angles, and they're all equal to 1/6. And that's a little bit obvious because this is what usually calls 60 degrees. It's 1/6 of the way around the circle. For a square, the turn angles at a vertex are all 1/4. This is 1/4 of the way around. Less obvious is for the pentagon, the turn angles are all 3/10. The general formula is that if you have a regular p-gon, so p equals sides, and a turn angle of tau at each vertex, then tau turns out to be 1/2 minus 1/p. So when p is 3, we get 1/2 minus 1/3, which is 1/6. When p is 4, we get 1/2 minus 1/4, which is 1/4. And when p is 5, we get 1/2 minus 1/5, which is the same as 5/10 minus 2/10, or 3/10. So this is really the basic formula that establishes what the turn angle is for a regular p-gon. The turn angle tau is 1/2 minus 1/p. And let me remark again that this is with this normalization that turn angles are normalized so that all the way around is 1. Well, let's have a look at the regular pentagon again. Okay, so there's our pentagon, and we have these turn angles of tau at each vertex. Now, also I've shown you these kind of wedges emanating from each vertex, and we have to explain what these wedges are. So this wedge here is obtained by taking 2 sides which are perpendicular to the 2 sides of the pentagon which meet at that vertex. So this side here is supposed to be perpendicular to this edge of the pentagon, and this side here is perpendicular to this edge of the pentagon. So this is 90 degrees if you like. That's 90 degrees. In terms of turn angles, this is a turn angle of a quarter, and that's a turn angle of a quarter. So if we denote this turn angle by mu, then tau plus mu has to be a half. Why is that? Well, because all the way around is 1, and this is a quarter, and that's a quarter, and the quarter plus a quarter is a half, so that leaves a half left over. So these add up to a half. That means that tau plus mu also have to add up to a half. And this same pattern is repeated at each of the vertices, so we have these 5 sort of wedges emanating out here. And the other crucial observation is that 5 times mu is equal to 1. That's because these wedges, if you think about their position with respect to each other, these two sides here are actually parallel because they're both perpendicular to this edge here. So that means we could fit these together so that this and this are exactly lined up without having to rotate either of them. That means that this turn angle plus this one plus this one plus this one plus this one are actually all adding up to going around once, which is 1. So 5 times mu equals 1. Now these two equations are all that we need to establish that, first of all, tau equals 1/2 minus mu, and from this equation mu is 1/5. That tells us that tau equals 1/2 minus 1/5. That's the formula for the pentagon. Now for a regular p-gon, it's exactly the same story, but we just replace the 5 by the p. So this tau plus mu relation equals 1/2, that'll still be the same, but now it'll be p times mu equals 1 if there are p such little wedges, and then tau will be 1/2 minus 1 over p. If you want to know a little bit more about working with turn angles, you can have a look in the algebraic topology series, where I show how these notions are very useful for curvatures of polygons, polyhedra. Okay, so now we have the situation where we have a regular polyhedron with Schlafli symbol PQ. I remind you that means that each face is a regular p-gon, first of all, and Q of them meet at every vertex. That's what this means. So we're supposing that we have that relation, and we want to figure out what are the various possibilities for P and Q. This is the way that we're going to approach the classification problem. So it's instructive to start with the planar case. So let's assume that the polyhedron is actually planar. So we're talking about a bunch of polygons, regular polygons in the plane, that have the property that each one is a regular p-gon and that Q of them meet at every vertex. We just want to explore what are the various possibilities for this kind of arrangement. So if we look at any one vertex, any one of these little pieces is part of a p-gon. So that we've just determined that that means that that turn angle there is 1/2 minus 1 over p. Similarly, this turn angle will be 1/2 minus 1 over p, and that's 1/2 minus 1 over p, and so on. And altogether, there are Q of these wedges coming together because we're assuming that there are these Q p-gons which are meeting at the vertex. Well, that just means that Q times this turn angle, tau, has to equal 1 because all the way around, in this planar case, is a turn angle of 1. So Q times 1/2 minus 1 over p equals 1. That's the basic equation. If we divide by Q, and then bring the 1 over p to the other side, we get 1 over p plus 1 over q equals 1/2. A very nice symmetrical relationship between the p's and the q's. Now, p and q are supposed to be natural numbers. There are not a lot of natural numbers that satisfy 1 over p plus 1 over q equals 1/2. If p is 4 and q is 4, that's a solution. If p equals 3 and q equals 6, that's a solution because 1/3 plus 1/6 equals 1/2. If p equals 6 and q equals 3, then you get a half. And it's not too hard to convince yourself, and it's a great exercise to think about the fact that these are the only solutions to this equation where p and q are natural numbers. So we're getting a classification result just by looking at the integer or natural number solutions to this relatively simple equation that's coming about by analyzing what happens at one vertex when we have q p-gons coming together. And the three solutions that we've obtained correspond exactly to the familiar three regular tessellations of the plane. The tessellation into squares, 4 squares meeting at each vertex, or into triangles, 6 of them meeting at every vertex, or into hexagons, 3 of them meeting at every vertex. So we've very pleasantly dealt with the planar situation. We've classified regular tessellations of the plane. Now let's have a look at the situation in the sort of spherical or polyhedral case where we're having a polyhedron in space. So we're looking again at the situation where that's a vertex of our polyhedron, and at that vertex we're assuming that we have q p-gons which are coming together. So each p-gon has a turn angle of tau at a vertex, and there are supposed to be q of these around that vertex. Okay, so what happens now is that the sum of all these q taus, the sum of all these turn angles, is not going to be equal to 1 as it is in the planar case. If we cut the situation along one of these lines, then we can fold out this corner onto the plane, and there will be a gap left over where we've cut. That's telling us that the total angle that we have in this situation has to be less than 1. In the planar case, all the angles add up to exactly 1 turn, but in this case where we're actually in space and we have actually a real vertex, then the total angle around is going to be less than 1. And so the equation is that q times tau, and tau, I remind you, is 1/2 minus 1 over p, so that product has to be less than 1 in this situation. So it's a very similar kind of equation as we've just had, but now there's an inequality instead of an equality. And then when we divide by q and bring the 1 over p to the other side, we'll have 1/2 is less than 1 over p plus 1 over q, which we can rewrite as 1 over p plus 1 over q is greater than 1/2. So if we have such a convex polyhedron where there's q p-gons meeting at each vertex, then necessarily p and q have to satisfy this inequality. And pleasantly, there are not a lot of natural numbers p and q that satisfy this. Because if the p's and q's are too big, then the 1 over p's and 1 over q's are too small, and they're going to not add up to something that's bigger than 1/2. So the p's and q's have to be relatively small to make this work. And there are some solutions. They are p and q equals 3, p equals 4 and q equals 3, or conversely p equals 3 and q equals 4. Obviously the situation is symmetric with respect to the p's and q's. Or we could have p equals 3 and q equals 5. If we go to p equals 3 and q equals 6, then we're already at the equals 1/2 situation, which is the planar case that we've already seen. And if we go to 4, 4, then we also get 1/2, which is also the planar case that we've already seen. So it's pretty obvious that these are the only ones, but convince yourself of that if we jack up the natural numbers more, then it's not going to work. What about p equals 2 or q equals 2? Well, a p-gon with 2 sides isn't a proper polygon, so that's not allowed to work. And we're not allowed to have 2 things coming together, because that's basically then the edge is just being absorbed. It's not a real proper vertex. So we have 5 solutions, and these 5 solutions correspond exactly to our Platonic solids. And this is really sort of the core part of the argument of why there are this finite list of Platonic solids. Now logically though, we're not really finished though, because we have some extra things that we actually have to do. So to complete the argument, we need to show, first of all, that each solution, like say 3, 5, actually corresponds to a real live mathematical object. In other words, we have to show that there really is a regular polytope that has these numbers. The argument is so far that if we have a regular polytope with the p and the q as the Schlafli numbers, then p and q have to belong to a certain finite list. We still have to show that if p and q satisfy this finite list, then there actually is a bona fide Platonic solid with those numbers. And then we also have to show that there's actually only one such solid for each solution. It's not entirely obvious that even if you do construct a solid made out of triangles, where 5 of them meet at each vertex, that there's only one such thing. Is that entirely obvious? I mean, maybe you could sort of make one that goes this way, and maybe you could make one that kind of wanders around a little bit different fashion. There's an argument to be made here which is, well, it's a little bit subtle. So these arguments can be made on physical grounds, relying a lot on pictures and our geometrical intuition. But purely mathematically, this is much more challenging. And in fact, there are very serious logical problems with some of these polytopes. Alright, so let's talk about mathematical constructions of these objects. Not physical constructions, but mathematical constructions. The easiest one is probably the cube. Because we've drawn it enough times, we know exactly where it should be. In terms of a coordinate system with x, y, and z coordinates, and points represented as triples of numbers, we can capture the cube with this finite list. Actually, it's a set, finite set of points. The point 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, and 0, 1, 1, and 1, 1, 1. This finite set of 8 points really defines the cube. Mathematically, that is one way of defining a cube, and we've pinned it down completely precisely, combinatorially. There's no ambiguity whatsoever. There's still a question of interpreting and saying, well, where's the edges? Well, the edges will be certain 2 sets formed from these things. And what about the faces? Well, you can also interpret the faces in terms of subsets of this set. What about the octahedron? It also has a very simple and pleasant description in terms of a set. Now it's a set of 6 points. And the 6 points are also very closely connected with the axes. So there's x, y, and z as usual. Here's 1 in this direction and -1 in the other direction. 1 here, -1, and 1 up and -1. And basically what we're doing is just taking these 6 points, the points which are at the unit positions on each of the 3 axes and which are also at the negative unit positions. So 1, 0, 0 and -1, 0, 0. And 0, 1, 0 and 0, -1, 0. And 0, 0, 1 and 0, 0, -1. I hope you can see the octahedron kind of there. So for example, these 4 here could be regarded as a sort of equatorial square. This thing, vertex on top, this is the vertex on the bottom. That's one way of thinking about it. So this is a very finite, concrete presentation of the octahedron. It's really a definition of the octahedron. One could say this is what the octahedron is. Of course, it's no longer a solid. Okay, it's mathematically, it's specified in such a way that you can obtain obtain the notion of what the solid is from these points, but the solid itself is not really captured directly, just perhaps indirectly. The same as with the edges and the faces and various other things. They're all sort of indirectly contained in here. You have to construct them by making certain combinatorial constructions involving these fundamental building blocks. But there's no question that these definitions really nail down the cube and the octahedron, and they do so in a very pleasant way that strongly suggests how to generalize these notions. So this way of representing the cube allows us to generalize it very easily. You could imagine extending things to 4 points. Okay, you might like to think then what a 4-dimensional cube looks like. And it's not hard to just sort of mimic what we're doing here, and then combinatorially, explicitly, you've created a 4-dimensional cube. And similarly with the octahedron, there's nothing preventing us from doing these constructions in higher dimensions. So this is a very attractive way of thinking about these two families of objects. They're really not just single objects, they're belonging in families that grow in dimensions. In fact, one should also think about what the 2-dimensional cube and the 2-dimensional octahedron is, and you should also think about what the 1-dimensional cube and what the 1-dimensional octahedron also are. What about the tetrahedron? Well, we've seen that we can construct a tetrahedron if we can construct a cube, because the tetrahedron can be thought of as being 4 points inside the cube. So that would certainly be one natural way of defining what a tetrahedron is in terms of the prior construction of the cube. But it's not really the best way, perhaps, of thinking about what a tetrahedron is. So there's another way which actually involves going up in dimension. Okay, so here's another way of thinking about what a tetrahedron is, but it involves 4-dimensional space rather than 3-dimensional space. So here's a picture of 4-dimensional space with an x-axis, a y-axis, a z-axis, and a w-axis. And let's say that these are the unit vectors in these various directions. Now you might say, well, wait a minute. 4-dimensional space, can we draw a picture of that? Yes, we've just drawn a picture of it. It's not really that much different from the way we draw 3-dimensional space on the plane by drawing the x, the y, and z, and sort of imagining that this other direction here is really the projection onto this 2-dimensional plane of this 3rd dimension. In the same story here, we're thinking about having a 4th dimension and we're just projecting everything onto this 2-dimensional plane. In terms of coordinates, we don't in fact have to be very creative geometrically with our insight. We just write down that the 4 points are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And so that actually defines the tetrahedron in the fashion of a family called a simplex. So this is a special case of a construction that pretty obviously works in higher dimensions as well. You can just always take the unit vectors, and that object, a collection of unit vectors, forms what's often called a simplex, which is a natural generalization of the tetrahedron. So the tetrahedron also belongs to this family of increasingly bigger regular objects. And geometrically, all the vertices here, and of course also then the edges and the faces as well, lie in a certain affine subspace of this 4-dimensional space. So all of these points have the property that the sum of the coefficients is always equal to 1. And this defines kind of an analog of a plane in 3 dimensions, but 1 dimension up. It's sort of a 3-dimensional slab in this 4-dimensional space. And the whole tetrahedron is actually contained in this 3-dimensional slab, which is telling us that we can actually see it in our 3-dimensional space. By the way we've constructed it here, this 3-dimensional space is really a sort of diagonally placed 3-dimensional slab in this 4-dimensional space. So this frees the tetrahedron from the dependence on a cube that we perhaps might naively guess is the way to define a tetrahedron. So that's great. We have the cube, the octahedron, and the tetrahedron. We have not just constructions of them, very explicit, but we also have ways of seeing them as parts of family as they go up in dimension. That's very nice. What about the icosahedron and the dodecahedron? Well, the reality is that that story is much more complicated. And although we can put something like this together and say, ah, look, here is the dodecahedron, this is just a physical representation. And actually, finding a mathematical representation of the same thing is extremely challenging. It's extremely challenging. And this may not be well understood these days because people write square roots with casual aplomb and not enough consideration about the real computational subtleties. Okay, so the arithmetic of the dodecahedron is intimately connected with the square root of 5. And the square root of 5 is a very problematic object, actually, because it has an infinite number of decimal places. And so you have to wrestle with this if you really want to understand the dodecahedron and the icosahedron correctly. And there's algebraic ways around that, but unfortunately, or maybe fortunately, the algebraic ways around it don't immediately correspond to this physical intuition that's represented by this object here. Okay? So there ends up being a gap between a proper mathematical representation, which we can create, and the actual physical object. They become separated by something. Okay? And there's a correspondence, but maybe we're no longer exactly talking about the same things here. So very interesting kind of a question here, and we'll talk a little bit about that later. But I want to, in our next video, come back to a different way of thinking about these objects, not so much as geometrical things, but as combinatorial objects, like sort of graphs or maybe two-dimensional versions of graphs. That's also pretty interesting, and there's interesting sort of approaches to classification from that point of view. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.